Hello, curious people. This video is about conservation of energy. There will be a follow-up video about power. In this video, what we're going to learn is how to apply law of conservation of energy to solve a variety of problems. These two examples here are shown as examples of conservation of energy. While these two people are sliding down, up here as they start to slide down, they have potential energy. And as they slide down at the bottom, they only have kinetic energy and velocities. So potential energy converts to kinetic energy here. And while for Lucas, who can jump up to 1 meter, pretty impressive for a small animal. Let's say he's starting to jump from the leaf leaping. In this case, he stores some energy in his springy legs, simply converted to kinetic energy. So I'm going to start with kinetic here. Has a velocity, has any kinetic energy, initial kinetic energy, and then jumps up, reaches to a height. At a height, he has a potential energy or gravitational potential energy. So he converts kinetic energy to potential energy, gravitational potential energy. In more details, initially, as he is gathering up his kinetic energy, he kind of stores energy in his springy legs. So he has kind of a spring potential energy, and then that converts to kinetic. So we are skipping that step. It's a pretty amazing job that this little guy is doing here. But he is using conservation of energy to convert kinetic energy to potential energy and jump as high as 1 meter. What is conservation of energy? The conservation of energy tells us that an isolated system's energy is conserved or remains constant. An isolated system means no work is done on the system. Nobody is pushing the system outside of the system or so on. There could be energy exchanges in between different types of energies, but no energy input from outside, or no energy take away. That system is isolated. As we're choosing our isolated system, we should be careful on what to choose. For example, for an object found on Earth, we could choose Earth and object to be an isolated system. For an object sliding on an incline and object with the Earth would be the isolated system. If I have a spring would be the isolated system with the mass attached to it. And if a mass on a surface and mass would be the isolated system. So we have to be careful as we're picking our isolated system. And we will be defining our system, apply conservation of energy. We learned that if there's a work done on the system, energy changes, and the total energy change in kinetic, potential. It could be thermal energy change, which mainly happens due to friction. That will be equal to work done on the system. We can use this full equation, write down initial and final kinetic energy, potential energy, and then we'll be looking at total change in thermal energy again, which will be the work done by friction. And write down an equation for conservation of energy. There's a different form of this equation in book. I'm gonna show it at the end as well. But this form I want you folks to use. So what we're gonna write down is if initial energy, where we will be adding all the initial energies. It could be kinetic, potential, spring potential, depending on situation, plus the work done on the system, if there's a work done on the system, minus any energy change to thermal energy, will be equal to final energy. Work here would be if someone outside is given some work on the system, and thermal energy will be generally energy conversion due to friction. Now in this will be our general equation here. If thermal energy, so there's no change in thermal energy, there's no friction, and there's no work done on the system, we can write down initial energy is equal to final energy. This is really what conservation of energy is. So this is what we mean by isolated system. There's no friction on the system, and there's no work done on the system will give us initial energy is equal to final energy. If there's friction, we'll look at the work done by friction will be applying it as thermal energy. I'm going to delete this guy here. Assume it's not zero. If there's some work done, we add it as plus. So initial energy will be changing by that much, and then we can still equate it to final energy. It's best to understand this with some examples, and this is what I'm going to do from now on. One example here, we have 3 balls. We throw them from the same height. This height is h here. With the same speed. So each has the same initial speed. And they follow different paths. Which ball has the greatest speed just before it hits the ground? We already know from projectile motion that they will all have the same final speeds, but we didn't really talk about why. If we calculate them using projectile motion, we will find that they will all have the same final speed if they were thrown at the same initial speed from the same height. But now we can say more clearly that if we use conservation of energy, initial energy is equal to final energy, we are ignoring the air friction or air drag, so there's no friction. Let me write down the full equation. So initial energy, if there's some work, will be changing. If there's some friction doing work against it, it will be converting some energy to thermal energy, and that will be equal to final energy general form. In this case, we have 0 and 0. So no friction, no additional work on the system. We say, okay, initial energy is equal to final energy. And as we see, we are throwing balls that have the same mass at different angles with the same speed. Each will have an initial energy, initial kinetic energy, which will be the same, plus initial potential energy, which will be from the same height, right? And then finally, they only have final kinetic energy. Final potential energy, I'll put this here, but it will be 0. Depending on the situation and the problem I'm looking at, there could be different type of energies, but in this case, we only have kinetic and potential energies. Notice here, actually, the balls are not necessarily same mass. I said same mass, but it could be different masses as well. If I write down my equations here, I'm going to write down the equations. 1/2 mv initial squared plus mgh is equal to 1/2 mv final squared. Let's say I call them m1, m2, m3, and so on, different masses. But notice that I don't actually need the mass. I can divide everybody by mass. So mass is not a factor, which is another thing we learned in projectile motion. And that will tell us that each of the ball will have the same type of equation, same type of energies before and after, initial and final. So each will have the same final speed. I hope that makes sense. Another question here, a hockey puck sliding on smooth ice comes to a 1 meter high hill, as you see in the figure. Will it make it to the top? That will depend on its initial energy. Now, sliding on smooth ice gives us the information that friction is ignored. Okay, friction. Alright, spelling error. Friction is negligible. Negligible. Alright, ignored. No friction. So if there's no friction, I can again start from here, but I know there's no friction and nobody's pushing on this puck anymore. Somebody hit it, gave it a velocity, speed, and it's going, so this guy is 0. No work is done on it at the moment, and there's no friction, no thermal energy. I can directly jump to initial energy is equal to final energy in any type of problem where no friction and no work done on the system. No forces is applied on the system. My system here would be the puck and the ice, right? Then I say, okay, initial energy is equal to final energy. If the initial energy here can be equal to final energy there, and when it's the minimum rule here would be that the puck goes up here and goes up to top and stops with 0 energy. If it not 0 energy, 0 kinetic energy. If it has a lot of energy, it could have some speeds here, but the minimum would be it would have 0 final speed. Gets up there and stops. That means it can make it to the hill. If it has more than that, it could be going on the hill too, but we are looking at the minimum possibility. That means initially it will have kinetic energy only, no potential energy. So U gravity initial is 0. And finally, it will have 0 kinetic energy, and it will have a final gravitational potential energy. And it will be mgh. I'm going to call this guy h here. 1 meters. So what I'm going to have is simply initial kinetic energy is equal to final potential energy. If the puck makes it there, it should be. But is it? Right? So we are testing that. So let's calculate the initial kinetic energy here. And I decided if it is equal to mgh over there, it can make it there with 0 speed at the top. If it's not, if it's smaller, right? If kinetic energy is smaller than the potential energy at the top there, it can't make it. If it is larger, it's even better. So minimum K initial should be equal to UG final. Could it be larger? Yes. But if kinetic energy initial kinetic energy is smaller than final potential, then it can't make it. All right? So we're going to check that now. Initial kinetic energy 1 over 2m v squared. Final potential energy mgh. I can't really compare them, calculate and compare them because I don't know the mass, but I can do the check right over here because mass cancels, and I can say, okay, is 1 over 2 v squared equal to minimum? It could be larger. Let's put larger or equal to g times h. Then I can calculate that as v squared over 2 times g. Notice I'm dividing both sides by g. And g cancels here. Is that larger or minimum equal to h? If that's the case, it can make it there. So let's see. What is RV? 4. I'm going to take 4 meters per second, square that. Divided by 2 times g is 9.8 meters per second squared. Is it larger or equal to minimum 1 meters? I'm gonna get 16 meters squared per second squared here, divided by 2 times 9.8 is larger than 16. 2 times 8 is 16. It's about 19.6 meters per second squared. That is not larger than 1. I'm dividing a smaller number by a larger number, so it can't make it. That doesn't work. That's not the case, so it can't make it up there. So minimum kinetic energy should be equal to potential energy. It could be also larger. If that was the case, it would have been able to reach up here, but it can't in this case because it is smaller. So we can say, since kinetic energy initial is smaller than U gravity final, Here we have only initial kinetic energy. Here we have only final gravitational potential energy. mgh. K final here is 0. Minimum. Initial kinetic energy 1/2 mv squared. Then, since this is the case, it can't go up there. It will maybe go a little bit and fall back down. Actually, I want you folks to go ahead and calculate this, and that's your duty. So apparently it can't reach up there, but it will reach to a height. What would that height be? What is the minimum height it can reach? So you will say it will come. At some point it will have 0 speed. It will slide back down, right? What is that point? What is that height? Where up to what height it can reach? All right. I almost calculated it for you. I put in the numbers, I just didn't find it. Please go ahead and find it. When it can reach to a height, you'll say kinetic energy initial, you gravity initial, that guy is 0, is equal to kinetic energy final, you gravity final. When it reaches to a point and stops, final kinetic energy is 0. So you'll use this to calculate the height, right? Go ahead and calculate that. It's actually done here. I didn't get the number. But what is the minimum height it can reach? And ask me about it. Calculate and ask me about it. So energy conservation doesn't mean energy cannot change from one form to another. It can change, as we see in the previous problem. We have kinetic energy converted into potential energy, and the puck goes high, a little bit higher, and then it stops there. We can see all different types of energy conservation, energy change, although the energy conservation of the system is maintained. This one is asking you to change the energy by rubbing something into each other, change the energy into a thermal energy form. We always rub our hands to each other to do that. When we are cold, it's because of changing our internal energy to kinetic energy first. We push our hands back and forth. And then that kinetic energy, since we have friction in between our hands, the friction does some work on our atoms, and our atoms starts moving faster. And then we feel the heat, because heat is more faster moving atoms in our hands. So this example is explaining how we can rub something to each other, two things to each other, and we can put a lot of atoms into motion. A lot of atoms into motion. That motion provides heat. One example here is lighting up matches. We put atoms into motion, they become hotter and hotter, and at some point they ignite the match. We can also make fire from rubbing two woods to each other, two sticks to each other. All the same ideas. Converting energy from one form to another. This is a similar example of energy conservation. We have a spring-loaded gun, shoots a plastic ball. So many of us played with these guns, I assume. Well, not me, but we push. Well, you guys did a projectile lab before, where you were pushing a ball into a projectile. It's a similar idea. So what you do as you push the ball into the gun, you compress a spring to an amount of X, so you store spring potential energy. And then when you let it go, that spring potential energy converts to kinetic energy and kicks the ball out at a final speed. That's the idea here. So you compress the spring to an amount of X, let it go. It will push the ball with a final speed of 2 meters per second. Energy is conserved, so energy initial is equal to energy final. I am jumping into this. Notice no work done, no thermal energy change because friction is not mentioned. There is no friction, even if it's not mentioned. Let's put it here. There should not be any friction. No friction. So I put these two guys to 0, then I directly jumped into initial energy is equal to final energy. Let me initially still write down the full equation. A initial, E initial plus work done minus delta E thermal equals E final. 0, 0, we jump down to this. Initially, we only have spring potential energy, nothing else. So I'm just going to put that guy down. Kinetic energy of the ball is 0 here. And notice here, my system is the ball and the spring in this case. So I'm considering what type of energy these two guys have. In the final, we only have kinetic energy of the ball. Now I could put here U spring initial, K initial plus U spring initial is equal to K final plus U spring final. If I want to be more systematic, set these guys to 0. But it's, well, I'm hoping it's pretty obvious to see that initially there is only spring potential energy. Finally, there is only kinetic energy. So I say spring potential energy here converts to kinetic energy and go. Skip the others. If you guys are confused, always start from here. If you can see that, okay, this spring potential energy is given to the ball as kinetic energy, you can start from here. Then you write down what you have. Spring potential energy is defined as 1 over 2 kx squared. That's equal to final energy 1 over 2 mv squared. Now I don't know K, I don't know M, right? So I can't really do much, but I know this. From here I get this. K x squared is equal to M v squared initially. Let's call this actually V1 first case. Now the question is continuing as, and then V1 is 2. So I got some information, but I can't really solve the question without knowing K, X, and M exactly. If the spring is replaced with a new spring, we're having twice the spring constant. Now I'm changing the spring. Second case, K2 becomes 2K. And the rest is the same, only new spring, I'm still compressing it as an amount of x, and so only K2 becomes 2K. X2 is still x. What would V2 be? In these type of cases, best thing to do, so since I already worked out the question, I know I'm going to get K2 x2 squared is equal to M V2 squared here. And only changing thing is K to 2K, so I'm going to put 2K x squared is equal to mv2 squared. Now, knowing this guy here and that guy, I can compare them by directly dividing them by each other. I can go by logic. Only K changed here to there. K becomes twice larger, and K and V is directly proportional to the square of K. Notice I have V squared here. That means V2 should be square root times V1. But that may not be easy to see. So I suggest you guys divide this by that. Once we do that, let me do it on this corner here. Once we do that, we will have this. Kx squared is equal to mv1 squared divided by 2 times kx squared is equal to mv2 squared. Cancel what cancels. I will have 1 over 2 is equal to V1 squared over V2 squared. I know V1 2 meters per second. I'm going to put that in here. Solve for V2. Working this out, please work out the algebra. You should find that V2 squared is equal to 2 times V1 squared, and V2 should be square root of 2 times V1. And V1 is 2. Once you do that, you'll get this answer there. Alright, conservation of energy. If energy doubles, speed is square root times the previous speed because of square root dependence here. This will be my last question here, and I'm gonna also post some more examples later on. This one would be like a regular classic energy conservation question. As we noted, a desert locust is an excellent jumper. Suppose a 2-gram locust, so I'm going to stop here. Mass of this guy is 2 gram. Convert to kilogram, divide by 1,000. I'm going 3 steps back, 0.002 kilogram SI units, remember? Leaving ground at 3.1 meters per second, so it's leaving ground. Wait a minute. Well, from here they say all right. Initial position is there. At the initial 3.1 meters per second, a speed that a desert locust can easily reach. A. If we ignore the drag force, there's air drag, we know, we ignore it. So no friction, right? Air drag works like friction. How high will the locust jump? I'm going to start here with the full equation. A initial will be A final. I can jump to that, but I will not. I'm going to write down the full equation as it's given. That I changed a little bit to make it make more sense. So I'll have an initial energy, not me, the locust. If there's a work done on it, we'll add that. If there's friction or air drag, there will be some energy conversion to thermal energy, so there will be a change in thermal energy. We'll take that away from the initial energy. And then we'll equate it to final energy. Initial and final energies are generally kinetic potential or spring potential. Work done will be if there's a force applied and pushing on the object. Again, if there's friction force, some energy will convert to thermal energy. We'll take that away, or drag force. Nobody is pushing or pulling on this guy. There is no drag force, so these are 0. Again, as we get more comfortable with this idea, we'll say, okay, no drag, no friction, initial energy is equal to final energy. These are, again, potential kinetic energies are added, also called mechanical energy. Initially, the locust is jumping from here, and remember, I can take this position to be 0 and ignore this part for potential energy. I'm going to be looking at how much potential energy change from that point to that point anyways, so it's safe to pick my 0 point to be this for my potential energy, and I will do that, and I will call this the height it will jump. Oh, let me go back here. The picture shows the jump distance to be that, so let's draw a new one that agrees with that. As it is jumping up, at the final position, it will have 0 speed, right? And the initial energy will be equal to final energy, no drag. Initially, the guy only has kinetic energy, no potential energy, but I'll put it here. This guy will be 0. Finally, the guy will have 0 kinetic energy and some potential energy. Call this just potential. I know it's gravitational potential, so I'm dropping this UG. Final kinetic is 0. So initial kinetic energy will be equal to final potential energy. That's the idea here. We'll say 1 over 2 m v initial squared is equal to mgh. We will always look at the difference in the height. Book takes it as y final minus y initial. I'll take it as h. That's the height. Notice I don't even need the mass here. Mass cancels. And I can solve for my height by dividing each side by g. I'm going to find height is equal to v initial squared over 2g. And that will give me my height. Initial speed 3.1 meters per second. I'm going to square that. Divide by 2 times g. And that will give me a height of 0.49 meters. Alright, part B is a little bit more interesting and involving. If 20% of the initial kinetic energy is lost to drag, how high will the locus jump? Now, 20% of kinetic energy, you guys know how we find 20%. We just multiply it by 0.20 times the kinetic initial. That much is lost. That means we'll calculate the kinetic energy and take away the 20% of it times that. That will be the kinetic energy left. Okay, so it says if there's drag, we put it into account and recalculate with that lost. How high will the locus jump this time? I want you folks to do that. It will be, of course, slower. Let's say it is this. Let me call this height 2. So if you calculate it and find a height 2 larger than height we calculated here, h, 0.49 meters, you did it wrong. But here's what you will do. As you write down the total energy conservation equation with everything, energy initial plus work done minus delta E thermal equals energy final. No work done, but now something is converting some part of energy to delta E thermal. That's the air drag. And it's given to us that that's equal to 0.20 times the initial kinetic energy. Given to us. If it wasn't given, remember, if we know the distance, so if it wasn't given, if I don't ignore drag, I look at the drag force, this drag force, right? And look at how much it goes. I can calculate how much work drag does, and it always works like friction. So it's work of drag will be negative, and that will be E thermal and delta E thermal, change in thermal energy. That's how we add that to here. And I can calculate it using drag force times the distance along with it travels, which will be h2 here, and that will be E thermal if it's not given, or delta E thermal, right? But it's given in this case, so I don't need to calculate it. And I'm going to write down initially I only have kinetic energy, potential is 0, and I have thermal energy to be 0.20 times that kinetic energy. Finally, I have 0 kinetic energy, and I have only potential energy now. I can calculate the height using the information given. And the height, well, this guy will be mgh2, right? Used all the information, calculate initial kinetic energy as a number, right? And that's initial kinetic energy is, we wrote it down, we didn't calculate it, but this guy over here, 1 over 2 mv initial squared. M is given, right? Initially we've seen it, converted to kilograms. We know V initial 3.1 meters per second squared. Get this guy, Get 20% of it. Input everybody. Solve for H2. All right. And you should find 0.39 meters. Find that. Good job. And if you get confused and stuck, please ask me in class or office hours. And I'll see you soon.